Hi, this is Rumi. I'm going to talk about congestion avoidance mechanism. There is a difference between the congestion avoidance and the prevention. Why actually prevention is needed? Because there is a excessive delay can be caused, and there may be resultant in retransmission of packet due to the dropping of packets. In case of UDP, packet losses are not recovered from, and so the main reason for a loss of packets in the internet due to the congestion, and the errors are very rare. Why congestion is needed? Because when the TCP increases the load to determine when the congestion occurs and then back off, so congestion avoidance has to be uh, taken care. And the losses are the event that determine the congestion. So in order to avoid the congestion, it is costly. But can we predict the onset of the congestion, prevent the loss? So in order to do this, there is a theme mechanism. So first mechanism here is DEC bit. It is the This is developed use on the digital network architecture, that is DNA. This is a connectionless network with a connection oriented, so it is used in the TCP/IP. The main idea here is the congestion control takes place between the routers and the end node. The routers will notify the destination whenever it experiences the congestion. So this notification implemented by setting a binary congestion bit in the packet. So it is named as a DEC bit. Whenever the destination host copies this congestion between the acknowledgement, it sends back to the source. Whenever the source receives this message, it adjusts in the source in the packets in order to avoid the congestion. In this source, what does it do is, it is when router congestion bit is added to the packet header, the router sends this packet if the average queue length is greater than or equal to 1. This average queue length is calculated as a busy plus idle, and then busy cycle. So the source response in this case here is whenever the router sends this congestion avoidance message to the source also maintains the congestion window. It watches if the fraction of the window's size is worth of packet resultant in the bit being set. If it is less than 50% of the packet being set, then it increases the congestion window by 1 packet. And if it is more than 50% or more, then packet congestion window will be reduced to 0.87 times. The increase by 1, decrease by 0.87 rule, it is a rule was selected because additive increase and multiplicative decrease makes the mechanism stable. Now, when congestion is perceived, it is calculated as a last busy plus ideal cycle plus ideal current busy cycle. This is shown in this graph. Whenever the router calculates the area under the curve and divides this value by time interval, it compares this average queue length. When the using queue length of 1, it triggers as the setting the congestion bit trade-off between the significant queuing. So that's the DEC bit. Now next mechanism here is random early drop. This random early drop, it is very similar to the DEC bit. The main difference here is that a DEC bit explicitly notifies about the congestion. Here in the RED, it implicitly notifies the source about the congestion by dropping one of its packet. In this, RED designed to use the congestion with TCP, which is currently detects the congestion by means of the timeout. So in this, the router drops a few packets before it has exhausted its buffer size completely. So what it causes a source to slow down the packets of packet sending in order to reduce the packet drops. So in this RED, it is easily adopted with the explicit feedback mechanism simply by marking the packets instead of dropping the packets. The principle in the RED is dropping of the packets. The next difference here from the DEC bit and the RED bit is how it will decides when to drop the packets and what packet it decides to drop. So in this RED mechanism, the drop of each packet's arriving packet with some drop probability whenever the queue length exceeds some drop level. The idea of this mechanism is called as a early drop random. In order to implement this mechanism, there is a RED algorithm is implemented. In this, first it will calculate the average queue length using weighted running average. It is similar to the TCP timeout computation. This average length is calculated as 1 minus weight into average length plus weight into sample length. Here the weight should be ranges from the 0 to 1 and sample length is the length of the queue. With this, it captures the average queue length is because it more accurately captures the notion of the congestion. Because this bursty nature of the internet traffic, it is quickly fill the fill the queue and it is quickly empty the queue. This is the nature of the bursty nature. This is the bursty nature of the internet traffic. So in order to do this, RED will maintain the two threshold, minimum threshold and the maximum threshold. This average length is calculated, it is compared with the minimum threshold and the maximum threshold. Whenever the average length is less than the lower threshold, then it will take no action. It will just queue the packets. When the average queue length is greater than the threshold, then it will drop the packets, arriving packets. Whenever the average length is between the threshold, then it calculates the probability, and based on this probability, it will drop the packets with that probability. Now how this drop probability takes place here is, whenever the probability of the drop increases slowly when average length is between the two threshold, reaching a maximum P. And whenever this when the this drop probability reaches the maximum threshold, then it will drop all arriving packets whenever it reaches the maximum threshold. So to do this, the temp is calculated as gives the both average length and how long it has been since the last packet was dropped. It is calculated as a temp P. This temp is a variable that is plotted on the y-axis, and the queue length is calculated between the two threshold of average length. Whenever the P increases slowly as count increases, thereby making the drop increasingly likely as the time since the last drop increases. This makes a closely spaced drop relations between likely than widely spaced drops. This extra step, including the P, was introduced by the inventors of the RED. Now, third mechanism here in this congestion avoidance is source-based congestion avoidance. In this, having unlikely the other mechanism, which is dependent on the new mechanism in this order, here in the source-based congestion, it is incipient the stages of congestion before the loss occurs from the end of the host. This is called as a source-based congestion window. So there is a mechanism like TCP, that is a TCP for the size of congestion is a TCP Vegas. The general idea in this technique for using the source-based congestion here is some router's queue is building up and congestion will happen soon if nothing is done about it. For example, source may notice the packet queues build up the network router. There is a measurable increase in the RTT for each successive packet. One particular algorithm observes this. When the congestion window normally increases the TCP, but every 2 round trips delay, algorithm checks if the RTT is greater than the average of minimum and maximum RTT. So the next algorithm does something similar, but the decision is whether or to change the current window size based on the changes on both the RTT and the window size. And another mechanism used for this is every RTT increases its window size by 1 packet and compares the throughput achieved to throughput whenever the window is one packet smaller. And the fourth mechanism here is algorithm is TCP Vegas. The intuition behind this TCP Vegas is a trace of a standard TCP. This is the second algorithm. Whenever the RTT increases congestion window by one packet, it compares this with throughput as the number of outstanding bytes divided by RTT. The difference between this current throughput and this above tagged throughput is less than half, decreases the congestion window by 1. And the last mechanism is TCP Vegas, that is TCP source maintains what is known as a base RTT, and the RTT when the flow is not congested, typically the minimum of all RTT subs out. Then source first it defines a given flow base RTT to the RTT of the packet when the flow is not congested. TCP Vegas sets a base RTT to the minimum of all measured round trip times. It is commonly the RTT of the first packet sent by the connection before the router queues increases due to the traffic generated by this flow. So this expected throughput is given as expected rate is equal to congestion window by base RTT. Second, TCP Vegas calculate the current sending rate and actual rate. This is done by recording the sending time of the distinguished packet and recording how many bytes have been transmitted within the time of the packet is sent and when it is acknowledged is received. And this computing sample RTT is distinguished. So this calculation is done once per round trip time. So the third thing to compute is actual rate with expected rate and adjust this window accordingly. This is given as difference is equal to expected rate minus actual rate. So in this there is a two threshold defined, that is alpha and beta. That is corresponding to having a too little and too much extra data in the network. When the difference between this difference that is calculated as expected rate and the actual rate, when this difference is less than alpha, TCP Vegas increases the congestion window linearly during the next RTT. When this is less than the beta, and the TCP Vegas decreases the congestion window linearly during the next RTT. And when it is between the two threshold, then last Vegas congestion window is unchanged. This graph gives the TCP Vegas congestion avoidance algorithm. This graph traces the congestion window, showing the same information as the graph traces given through the other mechanism. The below graph traces the expected and actual throughput rate and governs how the congestion window is set. In this graph, in this, the above colored line, that is green line, it gives the expected throughput, and black line gives the actual throughput, and shaded area gives the alpha beta threshold. The goal is to keep the actual rate between these two thresholds within the shaded region. Whenever the actual rate falls below the shaded region, the TCP Vegas decreases the congestion window because it fears that too many packets that are being buffered in the network. Likewise, whenever the actual rate goes above the shaded region, then TCP Vegas increases the congestion window because it fears that it underutilizes the network. Because of this algorithm, it compares the difference between the actual and the expected throughput rates to the alpha and beta threshold. These two threshold defines the in terms of kbps. So finally, finally it says that TCP Vegas decreases the congestion windows linearly, seemingly in conflict with the rule that multiplicative decrease is needed to ensure this stability. So this is the congestion avoidance mechanism. Thank you.